Okay, welcome everyone. So thanks for coming to my talk. So today I'll be telling you about efficient poly 1 over epsilon time partition oracles for planar graphs of bounded degree. Okay, so this is joint work with C. Seshadhri at UC Santa Cruz and Andrew Stolman, who is at Katana Labs. Okay, so let me begin by introducing the cast of characters relevant for today's talk. Okay, so the most important member in my cast are planar graphs. So these are graphs that you can draw in the two-dimensional plane without any of its edges running into each other. Okay, so for example, the graph pictured here on this slide is planar, though I have made a bad drawing of this graph. You can fix it like so. Okay, so this confirms that indeed this graph is planar. So today I'd be interested in only planar graphs of bounded degree. So I will stop emphasizing this after a while. So all graphs in today's talk are bounded degree, and after a while I'll stop mentioning this. Okay. So also I assume that you are given access to adjacency list of like this graph, whose maximum degree is, let's say, at most 10. Okay, so you can access any vertex you like, and you can also access any neighbor of the vertex you want. Okay, so the prototypical planar graph of bounded degree is the root n by root n grid. And here is one fun fact about bounded degree planar graphs in general and the grid in particular. So the fun fact is the following. So these graphs, they are what is called epsilon k hyperfinite, where k is big O of 1 over epsilon square. So now what does hyperfinite mean? So it just means that you can break the vertex set of this graph into connected subsets of size at most big O of 1 over epsilon square by deleting very few edges. So you can delete only an epsilon fraction of edges and break the vertex set of this graph into pieces that induce connected components, which are really, really tiny. Okay. So this is eminently doable for the grid graph. So notice that like you can just style the grid graph with boxes of order 1 over epsilon by 1 over epsilon. And the number of edges that run between these boxes is at most big O of epsilon n. Okay. So another thing that I'd like to note is that these hyperfinite decompositions, they're not unique. Okay. So for example, let's make some room and let's move this hyperfinite decomposition over to the left corner. And now if you consider all the tiles sitting inside the leftmost column and you were to refine them like so, then like lo and behold, you're suddenly looking at a yet another tiling or a yet another hyperfinite decomposition. So let's contrast this with the previous decomposition that I gave you. So you can like clearly see that these hyperfinite decompositions, they're not unique. Okay. Now with this out of the way, let me describe the problem considered, the problem that I'd like to consider in today's talk. So here is what I would like you to do. I would like you to build for me a primitive which takes a vertex v as input, and then it runs in time just polynomial in 1 over epsilon, and it returns to me with respect to some fixed hyperfinite decomposition b, the hyperfinite piece p of v that contains the vertex v. Okay, so you're given as input a vertex v, and I want you to return to me the hyperfinite piece p of v, and I want you to do this in time polynomial in 1 over epsilon. Okay, so notice I am asking you to give me a local implementation of such a procedure, right? I allowed only polynomial in 1 over epsilon running time. So if you think about this, the problem as stated so far should kind of feel underspecified, right? Because after all, I want you to locally find some answer, and this answer has got to be consistent with some global answer. And this cannot be done without some pre-processing. So what kind of pre-processing are you allowed? Okay, so you're allowed some very mild kind of pre-processing. You're allowed access to a read-only random tape, okay, which contains a number of bits which is just linear in n, or n times poly 1 over epsilon many random bits. Okay, so you're allowed access to this read-only random tape, and then you're supposed to implement this local procedure for me. Okay. So the thing that you might be wondering right now is that why should you care about such a goal, right? So here are a bunch of reasons why you might care about such a goal. So first off, as noted by Hasidim, Keller, Nguyen, and Onak back in 2010, partition oracles immediately give you property testers for planarity. Okay, so in particular, Hasidim et al. Used partition oracles to give the first exponential in 1 over epsilon time complexity testers for planarity. And then later on, Levy and Ron back in 2015 refined the partition oracles of Hasidim et al. To give testers for planarity that ran in time quasi-polynomial in 1 over epsilon. Also, you can use this tool, the partition oracle tool, to estimate a whole bunch of graph parameters like max independent set, main vertex cover, etc. for bounded degree planar graphs. So what you do here is that you break your graph, you break its vertex set into these pieces using your partition oracle. And then for any given piece, you can just find the size of the max independent set or whatever parameter you're interested in, and then you just scale back the answer. Okay. And curiously enough, like this primitive, partition oracle primitive, also helps you to obtain testers for all planar properties, including the undecidable ones. And this was a remarkable result shown by Newman and Soller, who did not give an explicit bound on the number of queries you need to test all planar properties. In a recent work with Sabyasachi Basu and Seshadhri in this year's SODA, we were able to show that in fact you can test all planar properties in time exponential in 1 over epsilon square using our improved partition oracle. Okay. So with that out of the way, let me flesh out the goal in today's talk a little bit more. Okay, so I wanted to implement this partition oracle, this local primitive. So since this primitive is local, one thing that you can note immediately is that for any vertex V, the size of P of V, the hyperfinite piece that V belongs to, is going to be at most polynomial in 1 over epsilon. Okay. And of course, you're trying to simulate access to some fixed hyperfinite decomposition. So it better be the case that the graph induced on P of V is connected. Okay. So I want these properties to hold with probability 1. Okay. But hold on, I was also given access to some read-only random tape. So what about the randomness of this tape? Where does that appear? So it's in the third item that the randomness is going to appear. So what I would like is, I would like the probability that the number of edges cut by the decomposition you get implicit access to. I want the number of edges cut to be small with probability at least 2/3. So I want this to be a legit hyperfinite decomposition with probability at least 2/3. And the probability is only in the cut bound. Okay. So this is the goal that I want you to achieve for me. Okay. So now let's see how previous approaches to this goal worked. Okay. So what Hasidim, Kellner, Nguyen, and Onak did back in 2010 is that they gave an implementation of partition oracles that ran in time exponential in 1 over epsilon. And Levy and Ron gave a refinement, and their algorithm ran in time quasi-polynomial in 1 over epsilon. So I will outline the partition oracle by Levy and Ron, which uses lots of ideas from the partition oracle of Hasidim et al. And the design principle behind both of these oracles is the same. And the high-level design principle is the following. So first, what you should do is that you should try to come up with a global algorithm to find a hyperfinite decomposition. Okay, so notice that you're coming up with a global algorithm that gets to see the entire graph, and this algorithm is allowed to run in time polynomial in n. And then in the second step, what you would like to do is you would like to simulate this algorithm locally. Okay. So now let me sketch the epsilon k partition oracle of Levy and Ron for you. Okay. So this algorithm, what it does is that it proceeds in L rounds, where L is just log of 1 over epsilon. And then you set your like initial graph, you call your initial graph to be G0. And then in the ith iteration, what you do is the following. You pick a bunch of random edges and you contract them all. So you merge the endpoints. Okay. So notice that each vertex in this graph corresponds to a subset of vertices in the original source graph G0. Okay. All right. And this way, like you understand it. So you note that each vertex in this graph corresponds to a subset of vertices in the original. And if some newly formed subset happens to violate the size bound, happens to have size greater than k, Levin and Ron just undo that contraction. Okay, they just unmerge. Okay. And now let me sketch the analysis of Levy and Ron. So their analysis is the following, that what you will have is that the number of edges that you cut in GI in the ith graph is going to shrink by at least a 0.99 factor as compared to the number of edges cut in GI minus 1. So after log of 1 over epsilon many rounds, you notice that the number of edges cut in the final graph is at most epsilon dn as we desired. Okay. And then Levin and Ron also notice that the time taken to find the piece that the vertex V belongs to in the ith graph is at most like the size k to the 2i, which you can notice is indeed quasi-polynomial in 1 over epsilon. Okay, so like that's pretty much there is to their analysis. I'd now like to make the following note. It does not appear that their approach is extensible to obtain poly in 1 over epsilon time partition oracles. Okay, so your pieces have to have size polynomial in 1 over epsilon. And in order to like get poly 1 over epsilon time testers, time partition oracles, you want to make L to be significantly smaller than log of 1 over epsilon. And that does not appear possible because the pieces have to have size polynomial in 1 over epsilon. So it seems that you do need new ideas. So this takes me to our work. And now I can describe what we do in this current work. So we develop a random walk based approach to designing partition oracles. So I'll show my algorithm on the grid graph. And so you take the grid and you take some vertex V inside the grid. And let PVL denote the distribution of over endpoints of an L length random walk started at the vertex V. So notice that this distribution has almost all of its support inside a Rutel by Rutel box around V. Okay, and therefore in particular, the 2 norm squared of this distribution is going to be at least 1 over L, roughly speaking, right? So I call such a vertex non-leaky. Okay, as the random walks from the vertex V get trapped in a tiny subset around this vertex. Okay, so this is remarkably different from the behavior you get in expanders, where the 2 norm of the walk vector will crash exponentially in the length of the walk. Okay, so this is true not just for the grid graph, by the way. This is true for like all bounded degree planar graphs. You should really think of grid therefore as the prototypical planar graph. So in particular, you can show the following lemma, that in any bounded degree planar graph, an overwhelming majority of the vertices, they are non-leaky. Okay, so that's one like very useful hammer, and like with this useful hammer, I am now ready to describe our global algorithm. So this lemma kind of suggests a global algorithm. I just like to introduce a little notation first. So fix some vertex inside your bounded degree planar graph and define C of S, the cut around S, to be the vertex S itself if the vertex is leaky. Otherwise, just declare it to be the L1 heaviators of the distribution PSL. I'll assume for the rest of this talk that you can find the distribution PSL exactly. It's not like a big leap of imagination. There is some error tracking that you would have to do. You would track only the vertices that are reached with good probability. So you track only the heaviators. And therefore, I'm going to assume that this routine C, the cut around S routine, is a deterministic algorithm that you can indeed implement efficiently. So let's make that assumption and move on. So now I can sketch our algorithm using the following picture. So here, like I assumed that I have this graph and I selected some 3 vertices and I found C of those vertices, the cut around those vertices, and I have shaded these subsets. Okay. The unshaded vertices, I will call them free. They have not been captured yet or clustered yet. Okay. So now let me just sketch out our algorithm. So our algorithm does the following, that it looks at the set of free vertices and the set of vertices that are free right now. And now you pick the smallest free vertex. And then what you do is that you find the cut around this vertex, namely this green set is what you find. And then you assign the piece discovered by this vertex S to be just the set of free vertices that happen to lie inside the cut around S. Okay. So P of S is just this set. Okay, the shaded set around S. And then you update the free set. Okay. So that's our algorithm. So while this algorithm appears to be a fairly natural algorithm, there are some challenges when you want to implement this algorithm locally. So the local implementations are not quite straightforward. So let's try to see what those challenges are. So first of all, you need to find the free vertex S that led to the capture of V. Okay. And then of course you want to find C of S restricted to the free set. So there are these 2 challenges that you need to deal with. Okay. And if you look at the second challenge, so this second challenge, we are able to handle this challenge using the following lemma. So this lemma shows the following, that as long as the free set is large, you would have enough vertices belonging to F for which C of S intersection F is also large. That is, you have enough vertices that would lead to the capture of many more free vertices. Okay, so the free set is indeed going to shrink rapidly. It's not that the free set does not shrink at all. The free set will shrink rapidly, and in some sense you could use this to handle the second challenge. But the major concern for us was the first challenge, right? I mean, how do you find the free vertex that captures V? So notice that you're given a bounded degree planar graph, and recall that random walks in a bounded degree planar graph are reversible. So that is, if an L-length random walk from the vertex S reaches a vertex V with good probability, then an L-length random walk from the vertex V will also reach the vertex S with good probability. Okay. So in order to find the vertex that captured V, you can just find the list of suspects. You can find all the vertices where the random walks of length L from V reaches with good probability. And now you need to check if any of these vertices captured V, right? But it could very well happen that some of these potential captors for the vertex V was not free, right? You need to determine whether this vertex was free or not free. That was a fairly big challenge for us, and we were not able to handle this challenge in any straightforward way. So what we did is that we modify our global algorithm, and here is our modified global algorithm. So initially you declare the free set to be all the vertices. And then what you do is that regardless of whether a vertex is free or not free, you run diffusions from every single vertex. So you have this vertex S, it may be free, it may not be free. Nevertheless, you run the C procedure from this vertex, find this green set, and you restrict it. Turns out that this routine can be implemented locally fairly easily. And it leads to polynomial in 1/epsilon partition oracle as we desired. So now I would finish up by telling you about future directions. So there is really a lot going on. So I'd be interested to see if there are more applications of partition oracles. So Levy and Shoshan found one. They were able to test Hamiltonicity on planar graphs. So under the promise that a graph is planar, they were able to develop a tester for Hamiltonicity using partition oracles. And it seems that these ideas can have also applications for distributed property testing, and there could be probably more distributed algorithms for planar graphs that you can find using partition oracles. Okay, so that's all I have. Thank you.